相对论的能量，只能算它的动能。你比如说，有两个复合粒子，其中的话，然后掉到一个粘性的滚筒上，就是这个滚筒的话会把这个 B 粒子给粘住啊，然后把这个 A 粒子给甩出去。在这样的过程当中，你就可以这个很简单的去计算，只要这个角动量只要这个滚筒的角速度足够大的话，那么这样子你可以把这个 A 甩出去的时候，A 它的机械能是比这个之前 A 和 B 加到一起的机械能可以还要大的。那么这个就是一个相当于super radiance 的这个牛顿的近似啊。那么在这个旋转黑洞的情况下也是一样的，因为旋转黑洞有一个叫所谓的参考系拖曳效应，就是说在黑洞旋转的时候呢，周围的时空啊，当然随便一个什么旋转物体都是这样的，只不过旋转的黑洞的话，这个效应非常明显，就是说在一个旋转的物体周围，时空也要跟着稍稍旋转一点。什么叫时空跟着旋转呢？这个时空我们也看不见摸不着，但是如果离着很远，有一个这个不旋转的物体啊，往这个旋转物体这儿掉的话，那么你就会发现掉到离这个旋转物体很近的时候，也就会开始跟着转。这个就是所谓参考系拖曳效应。那么对于正常的普通的物体而言，这个参考系拖曳效应是非常小的，因为它是广义相对论效应，并且广义相对论里边的高阶效应。所以说我们都可以忽略不计。但是呢，即使对于像中子星这样的这个高度广义相对论的系统，它这个效应都非常小。但是对于黑洞而言，这个效应是很大的。为什么这样呢？因为黑洞啊，就旋转黑洞的这个能层的这个表面，实际上就相当于就是旋转黑洞的话，首先它有外世界，有内世界，内世界就不管了，它外世界的外边呢，还有一个所谓的这个能层的表面啊，就是外世界和能层表面中间的这个区域叫做黑洞的所谓的能层。就是说，这个能层的表面它有什么样性质？就是说，你一个随便一个这个什么东西啊，你要是想在能层的表面，你要还想不跟着黑洞转的话，那你要以光速去反着这个黑洞旋转的方向跑，你才能不跟着黑洞转。就相当于就是你到能层里边的话，你就怎么着想不跟着黑洞转都不行，你必须要跟着这个旋转的黑洞转。也就是说，在旋转黑洞的时候，这个参考系拖曳效应是非常非常明显、极端明显的。这样子的话，那回到这样的一个这个半经典近似的这个物理图像的话，就相当于是你确实你这个比如说你 B 掉到能层里边的时候呢，就相当于你这个 A 和 B 这个系统，你就必须就是这个能层就相当于极端粘性的这样的一个表面，就让这个物体你不管是什么样物体，你必须要跟着走。然后这样子呢，但是能层的话可以计算，就是能层还不是世界啊，不是 horizon，就是说里边的东西你足够快，你还可以被甩出来。这样的话，你就可以一部分甩出来，获得巨大的能量。当然，这个东西的话这个是一个比较简单的物理图像，这个是可以去仔细的计算的。那么仔细计算的话呢，就要把这个不是科尔黑洞的这个度规写出来啊。当然，这个度规挺麻烦的，这个具体的形式的话，你要完全定量计算，当然很重要。但是在这里我具体讲的时候，它具体形式和我这个报告并不是那么的重要啊。那重要的一点呢，在这个彭罗斯过程里边，就是前边这个度规里边的这些系数都是不含时间的，所以说呢，这个度规呢也是有一个这个 Killing vector 啊，有一个这个坐标时的这个方向是一个 Killing vector。但是非常重要的一点就是坐标时方向这个 Killing vector，我们知道 Killing vector 就对应着守恒量嘛，就是说 Killing vector 和这个动量进行收缩，就是说只受引力不受其他力的作用的这样的粒子，它的这个守恒量。那么但是在黑洞背景下，这个守恒量非常重要，它不是一个 global time-like Killing vector，也就是说它在这个黑洞外边的时候。远离黑洞的时候，它是这个类实的，但是呢，跑到了能层里边，这个 T 就变成类空的了，这样子就非常有意思啊，就相当于这个我们根据对称性就有守恒量，所以说根据这个 time-like Killing vector，根据这个坐标时所导致的这个 Killing vector 的话，我们就有一个守恒的能量，但是这个守恒的能量啊，就是在这个黑洞外边的时候。你只要一开始把符号给定对了，在黑洞外边这个守恒的能量肯定是正的，但是到黑洞里边呢，这个到这个能层里边，甚至到黑洞里边， 因为这个 T-mu 不再是一个类实的矢量，它可以是类空的，所以说这个时候这个能量呢，这个所谓的能量啊，就是它是一个守恒量，就是这个所谓的用坐标时定义的能量，它就可以是正的，也可以是负的。这样呢，就会出现这样的过程，就是说我们一开始这个东西扔到黑洞，就是把这个东西复合粒子扔到黑洞里边的时候呢，然后呢，你这个往里边跑的这个粒子呢，它的这个能量，它的这个所谓的能量啊，就是那个守恒量，已经变成负的了。虽然说你局域参考系看这个粒子能量还是正的，但是它那个守恒量已经变成负的了。这样子的话呢，那既然它们俩加一起，这个 E1和 E2加一起是守恒的，然后这个 E1呢，那这个 E2变成负的，那 E1就大于本来的那个 E0，就是本来一开始往里掉的时候那个 E1加 E2了。所以说呢，那么这样子就是跑出来的这个粒子的能量反而变大了，这个就是所谓的彭罗斯过程。那么我们知道，在量子力学里边告诉我们，就是粒子啊，其实它也是有这个所谓波动性，也就是这个粒子你传播一个时间的话，它会变一个相位的，就是它有波的性质。那么很自然的，我们就会问，说是这个你既然对粒子有彭罗斯过程，那么对于波动是不是也有这个相应的彭罗斯过程呢？那么这个就是用这个波动，如果你一开始是考虑一个一列入射波啊。这个入射波呢，然后在黑洞的这个能层里边呢，就是一部分的入射波掉进黑洞，哎，反而这个出射波的这个幅度啊，振幅反而被增加了，就是这样的过程。这个对于场或者对于波动来讲呢，这个是叫做兹尔多维奇过程。但是这个兹尔多维奇过程，它只是说如果你对于没有质量的，比如说对于光啊没有质量的矢量场或者没有质量的标量场的话呢，因为它们的波动都是以光速传播的，所以说呢，就是你这个东西这个波动跑进来，然后被黑洞给amplify 给这个振幅给变大了一下，然后呢它又跑走了，这样子的话你就不能反复的把这个振幅给加大。所以说这样子的话，这个就是所谓一锤子买卖啊。那么有没有可能说通过这个旋转的黑洞，然后你把这个波动的振幅反复的加大，最后达到一个这个从黑洞里边显著的提取能量，有没有可能做到这样呢？那么首先大家就想到啊，这个你比如说你把那个就是跑掉的那部分的光啊，你拿镜子给收集起来。然后再把镜子上的光再反射回来，这样子的话呢，你就会提取旋转黑洞的能量，让这个里边的系统越来越热，然后这样就可以造一个所谓的黑洞炸弹。当然你也可以更加和平的利用，就是说你周围漏一些缝的话，然后那些非常热的光出来，那么这些光你就可以拿它，比如说发电呢，这样子的话，是不是你用这个照镜子的方法就可以获得能源？这样子可以产生这个黑洞文明啊？当然这些都是非常科幻的一些想法，并且这些都是非常人工的 artificial 的，就是说我们也会想问这样问题：有没有可能在自然界里，你不需要这些人造的物体，就产生等效的，像镜子一样，把这个辐射，跑出来的辐射又收集回去，让这个黑洞继续，把这个辐射进一步的 amplify，有没有可能，有这样的现象呢？非常有趣的是，在自然界里可以真的有这样的现象啊。那么这个现象就是所谓的黑洞的超辐射，就是说前面我们说，如果要是没有质量的粒子的话，哎，那这个粒子你辐射出去以后就跑了，就回不来了。但是如果是有质量的标量场，当然这个质量呢，我们考虑就质量相对比较轻，所以说它如果大概的来讲，在离黑洞很近的地方看的话，好像它像光差不多的，就是它可以这个掉进去之后呢，然后像无质量场一样，就是那个体现很强的波动性，然后被amplify 一下，然后跑出来。但是呢，当它跑到一定距离的时候，就是你考虑比较长的距离的尺度的时候呢，它的质量的效应就体现出来了。那么这样子的话，就是它就被这个黑洞吸引。如果它的速度不足以达到逃逸速度的话，哎，那它又掉回来，然后又继续被黑洞给 amplify 啊，然后又甩出来，然后又掉回去，又甩出来，这样的一系列的过程。那么这样一系列的过程呢，就会使得在黑洞周围啊，就自发的，只要是一个旋转黑洞，然后只要世界上 存在这样相对比较轻。相对比较轻的意思，就像我说，就是你只有在离黑洞比较远的这个尺度上，你才会这个黑洞的这个标量场的质量才会重要，就是这样的场啊。所以说，也就是这个场它的康普顿波长是要大于这个黑洞的世界半径的。就是但是也不要大太多，大太多的话，这个循环就会变得非常慢。这样子的话，在黑洞周围长出这样标量场的气体就会非常的慢。所以说呢，就大一点还大不多，康普顿波长比这个黑洞的世界半径大一点，还大的不是很多。在这种情况下呢，这个过程就会有效的非常往复的出现，然后这样呢，就会使得这个黑洞周围环绕着这样标量场的这样的气体，就好像是黑洞周围生出了这样的气体啊，就好像黑洞生气了一样。那么这个就是所谓的黑洞的超辐射。那么这个呢，其实在黑洞周围的，待会儿我们会看到啊，这个它的解呢，实际上就和一个原子是非常像的，所以说这个也通常被叫做引力原子。那么这里就是说，我们为了简单起见，我们考虑这个标量场。其实一般的玻色子都是可以的，比如说矢量场，有质量的矢量场也是可以的，或者有质量的这个高自旋的场。但是费米子场就不行了，费米子场是没有这样的超辐射效应的。好的，然后这个所以说呢，就是你如果黑洞周围能生这样的气的话，那么假如说我们考虑真空中一个旋转的黑洞，周围也没有任何干扰，也没有任何伴星，那么在这种情况下呢，那么这种黑洞所谓生气，就是所谓这个 super radiance 啊，这个更加学名的叫法叫超辐射。那么黑洞超辐射的全过程就是说，一开始这个黑洞形成的时候可能有角动量，然后黑洞的吸积呢，有可能让这个黑洞持续的有角动量，甚至角动量变得越来越大。然后在这个情况下呢，就是说这个旋转的黑洞就可以逐渐的开始外边积累这个超辐射啊。就是假如说这个宇宙中存在质量合适的这个标量场的话，那么就积累这个超辐射。然后呢，黑洞周围的这个超辐射，它会向外辐射引力子，然后这样子的话呢，就逐渐的衰变。这个衰变是非常非常缓慢的，就是很容易就是宇宙学尺度，甚至比宇宙年龄啊还就是可以比拟，甚至你不同的黑洞大小的话，甚至可能比那个时间还更长的这样的尺度呢，通过这个引力辐射逐渐的衰变。那么这个就是黑洞超辐射的这个现象。但是呢，如果这个待会儿我们会讲，就是如果要是周围有一个伴星的话，那么这个过程其实会大大的加快。好的，那么下面我们就来讲这个黑洞周围有一个伴星的这样的情况。这个黑洞周围有伴星的情况下呢，这个我们要讲两件事情啊，一件事情是回顾之前别人的工作，主要是丹尼尔·鲍曼等人的工作，然后之后呢讲我们的工作。这个回顾的部分我就简单的讲一下吧，就是说鲍曼等人呢在2019年他们这个有一篇文章叫所谓 Gravitational Collider Physics， 也叫 Collider Physics， 就挺好玩的。那么这篇文章他们的主要的目的呢，就是说，哎，黑洞周围的这个超辐射呢，它就是既然它像一个引力原子一样，那么这个引力原子的话，它就应该有一些固有的频率啊，就是一个状态有一个频率，另一个状态有另一个频率。然后，如果要是这个伴星绕着黑洞转的这个周期呢，如果和这个两个频率差基本上吻合啊，就是中间还差一个角量子数，反正他们俩就是差不多的时候呢，就差某一个倍数的时候呢，这个时候就有可能发生共振现象。那么发生共振现象的话，就可以使得这个黑洞的这个引力原子的态从一个态呢共振的跃迁到另一个态。那么这样子的话，就是会导致说是通过这个反作用呢，会导致这个伴星，比如说另一个黑洞呢，它的轨道或者是很快的掉到另一个轨道，就取决于这里边的是向上跃迁还是向下跃迁啊。那么就会或者是这个给这个外边的这个黑洞额外的能量，或者是这个吸收这个外边黑洞能量。这样子的话呢，如果给外边黑洞额外能量，就会使得这个外边的这个黑洞它停留在原本的轨道上更长的时间。就是因为这个黑洞的外边黑洞通过引力辐射会逐渐的往里掉嘛， 但是如果要是中间伴星给这个黑洞能量的话，它就会悬浮在一个轨道上，虽然发生引力辐射，但是也悬浮在一个轨道上，相对更长的时间，这个叫所谓 floating orbit。然后呢，如果要是说这个黑洞旁边的这个标量场是从低能级向高能级跃迁，它要吸收能量的话呢，就吸收了伴星的能量，这个伴星就会很快的从一个比较小的、比较大的轨道半径，很快掉到一个相对小一点轨道半径。那么这些现象呢，原则上都可以在未来的引力波的观测当中去寻找。比如说，未来 LISA 是可以找很多的这样的系统的，包括这个像天琴、太极，可能都会找很多这样引力波的这个双黑洞的系统。那么他们有可能都可以去看这样的引力所谓的 gravitational collider physics 这样的跃迁。那么在他们工作之后呢，我们也做了一个相应的工作啊，就是我们指出，如果是一个黑洞和脉冲星系统的话，那么因为我们知道脉冲星，我们是可以非常准确的测它的这个脉冲到达我们的时间的，这个比引力波的测量应该是要准确很多。所以说，未来一旦是可以找到黑洞和脉冲星的这样的双星系统，现在还没有找到啊。未来如果能找到的话呢，它会对这个所谓 gravitational collider physics， 也就是说伴星导致黑洞里边状态跃迁，会有可以有非常精密的这样的测量，特别是就是主量子数的跃迁，还可以测量精细结构和超精细结构。好的，这个就是我花了接近一半的时间做的一个 introduction 啊。然后接下来呢，我这个主要讲两部分，一部分是这个科尔黑洞周围就是有标量场，这个具体怎样计算。然后另一部分我就讲一下我们 termination of superradiance，就是说周围有伴星的话呢，可以使黑洞周围标量场衰变这样的两个部分啊。然后这个至于说鲍曼他们的这个工作就是 GCP transition。gravitational collider phase transition 和 pulsar timing 这两部分呢，我就非常简单的一语带过了。首先黑洞 superradiance 这个领域的话，我刚刚开始学的时候，我就觉得它这个符号约定让人很头疼。但是所以说我首先向大家澄清一下这个符号约定啊，就是说标量场的质量，我们用这个 mu 来表示。就是黑洞外边就是所谓生气啊，就是产生的那个cloud 那个场的质量是用 mu 来表示的。然后呢，这个黑洞的质量是用大 M 来表示的，但是这个小 m 不是质量，小 m 是这个所谓磁量子数，就是说把这个给写成 YLM 里边的那个 m。那么，然后呢，这个小写的欧米伽是频率的意思啊，是这个就是 e 的负 i 欧米伽 t 那个频率，然后大写的欧米伽是黑洞外世界的这个拖曳速度，也就是说，在这个零角动量粒子在这个世界上的角速度。好的，那么那么我们这个首先也是从这个科尔黑洞的背景写起，就是首先有这样的一个度规科尔黑洞，然后呢，我们就可以在科尔黑洞的背景下写标量场的克莱因高端方程。有各种各样不同的这个速度啊。其中，因为非相对论其中一个相对比较快的参数，这样子的话呢，我们就可以就相当于你要半经典的，就是说，如果把这个标量场看成某种半经典，想象成半经典粒子的话，它在黑洞周围跑的那个速度，是要比这个标量场自己内在的频率要慢很多的。所以说，我们把这个慢的速度，对不起，把这个快的频率给分出来。然后前边的这个波函数呢，就只带这个慢的这个频率。然后这样子的话呢，我们就可以把这个东西带进克莱因高等方程。带进克莱因高等方程之后，这个两阶的时间导数，它就会被这个缪平方那项所主导。所以说，两阶时间导数就变得不太重要了。这样子的话，你剩下的那个一阶时间导数的项，得到的就是一个等效的薛定谔方程。 然后那些相对论的那些项，就两阶时间导数什么那些项呢，可以当做微扰，再给加到这个薛定谔方程里边的这个相对论修正里边。然后再有我们知道科尔黑洞啊，它不完全是一个平方不完全是一个这个一次方反比的势能，它还有一些像转动的项啊，然后还有广义相对论修正的项啊，然后所有这些东西都放到这个所谓相对论修正里边。这样我们就得到了一个，其实就是这个薛定谔方程啊。前面我们说了，它是一个一阶时间导数的方程，然后这个空间导数还是二阶的克莱因高顿方程里边来的。然后呢，因为你远离科尔黑洞的部分，它就可以就是相当于是一个就是牛顿引力了。所以说的话，它就是一次方反比的势能，然后剩下的就是相对论的修正。这里呢，我们就也不是我们了，就是大家啊，就引入了一个这个所谓的引力的精细结构常数阿尔法。这个引力精细结构常数就是牛顿引力常数，然后黑洞的质量和标量场质量它们的乘积。这个无量纲的参数就是在自然单位之下无量纲的，要不然除以 h·c 以后无量纲的参数呢，它就和那个氢原子的那个精细结构常数它起的作用是一样的，都是在这个库伦式前边的这个数。那么这个数呢，就比如说要3倍太阳质量黑洞的话，那么如果让这个阿尔法是一个小于1，但是不太小的数的话，那比如说这个缪标量场的质量就是10^-12电子伏特。然后你要是对于更大的这个质量的黑洞的话，你相应的等比例的，你就要考虑更轻的这样的标量场。那么这个既然有了薛定谔方程，然后剩下的东西都是这个近似，都是这个在这个就是可以用微扰解来解。那这样薛定谔方程的解，这个都是非常成熟的，我们可以直接用分离变量的方法来解。然后呢，这个就是相信大家就直接在量子力学里边都学过了。但是对于黑洞的情况，它还有一个特殊的东西，就是说，在这个氢原子的薛定谔方程的时候，它在这个中心啊是一个正常的解，就是在这个在 r 等于0的地方，它没有什么奇异性。但是呢，对于黑洞而言，它是比较特殊的，就是我们没法给 r 等于0的地方的条件，所以说我们需要在黑洞的世界上，黑洞的 horizon 外世界上边，科尔黑洞的外世界上边，给这个入射的只有入射波没有出射波这样的一个条件。那么这样呢，就可以得到这个就是解出来分离变量的解里边的这个频率呢，这个频率是不仅有实部也有虚部。这是因为你这个黑洞的世界上边入射波的话，你这个波动可以进去嘛。所以说这样子的话，就并不是一个这个所谓的概率守恒的方程，它有些东西跑进去了。这样的话，这个欧米伽就可以有一个虚部，这个虚部是非常重要的。当然，这个具体的计算我这里就不讲了。然后它的具体计算就是相当于就解薛定谔方程里边，在镜像的这个常微分方程，你是要加这个边界条件的。然后你解出来之后呢，就有一个虚部啊。但是这里边要注意的，这个虚部里边这个因子和这个因子非常重要，前边都是一些数值因子，就是这个因子呢告诉我们什么？这里边就是说角量子数黑洞的这个参考系拖曳的这个黑洞转动的角速度和这个欧米伽，也就是说和这个黑洞的这个能量的对不起啊，和黑洞外边标量场超辐射的那个能量的实部，它们3个之间呢的关系决定了这个伽马，也就是说这个能量的虚部它的正负号。那么这个正负号是什么意思呢？我们的这个符号约定里边，伽马是正的，代表是有这个超辐射出来啊，也就是说，伽马是正的，代表这个解是指数增长的，然后伽马是负的，代表这个解是指数衰减的。也就是说呢，当这个黑洞的转动速度足够大的时候，这个伽马就是正的；如果黑洞转动速度足够小，伽马就是负的。它是和这个欧米伽除 m 来比较。好的，那么这个就是超辐射，这个是这个系数啊，就是有没有超辐射。然后这个超辐射的速度是这个因子，这个因子的话，待会儿我们还会翻回头来，是非常重要的一个因子。大家看这个因子是4L 加5次方，也就是说它对 L 的这个依赖是非常强的啊。因为阿尔法是一个，你比如说取0.1啊，或者说取有可能更小这样的值， 然后呢，如果要是说这个这个外边有这个标量场，然后指数衰减，可以是很大的数。就是这个待会儿我们说这个 termination of superradiance 是里边是非常重要的。好的，那么回到我们这个前面讲的这个啊，就是说这样呢，我们就可以把这些具体的状态给写出来。然后写出来之后呢，这个其中很多的状态，你比如说 L 等于0的所有的状态都是不稳定的啊，就是你外边本来你要是有这样的标量场的话，它也会指数衰减掉的。然后呢，这个第一个就是能量最低的这个超辐射的态是211这个态，就是211这个态就相当于你只要这个宇宙中存在这样标量场，也存在旋转的黑洞呢，这样的态就会被自发产生出来。然后还有这个311、322，像这样的态呢，都是一些可以发生超辐射的状态。然后你在下边，你比如说什么你像200啊什么的这样的态呢，都是不稳定的。然后这个是也是借用鲍曼他们文章里边的一个表格，就是说呢，对于标量场而言，就是211这个态它最多可以有多少呢？211这个态它最多可以有这个 of order alpha，这个阿尔法就是前面我们说的那个引力的星体结构常数，它可以取比如说像0.1这样的值，也就是说，如果一开始考虑一个极端的旋转黑洞的话，那这个从极端旋转黑洞提取出来的这个能量可以有多少呢？可以有这个黑洞能量的0.1倍，这么多。这个也就是说，黑洞周围就是这个超辐射啊，这个所谓生的这个气标量场可以是非常多的。然后如果 m 等于2 m 等于3的态，相应的就要变少了。然后这个矢量也是可以相应的去做计算的。然后这个是比如说211这个态啊，211这个态和312这个态，它的这个增长率是这个样子的。然后它的衰变率，它的这个衰变率是通过辐射引力波衰变的。所以说辐射引力波的话，它额外的要有引力相互作用。然后大家可以发现它的这个就是它的寿命都可以是非常长的。所以说呢，这个态一旦产生出来，那么它在黑洞周围就可以存在很长的时间。这个都是说，如果黑洞周围没有伴星的情况啊，然后这个黑洞周围如果有伴星呢，就可能发生两种情况，一种情况是共振，参数共振，这个因为时间关系我这里就不讲了。然后的话，我们主要讲我们这个工作，就是黑洞周围有伴星的时候呢，它可以让这个前面我们讲的这个轴子云，就是或者说氢标量场的这个云，让这个引力原子变得不稳定。为什么黑洞周围的超辐射可以让引力原子变得不稳定呢？就是这个就是一个示意图啊。比如说我们考虑这个322这个态，考虑322这个态，然后呢要旁边就是远远的啊，待会儿我们看就可以很远，就是旁边很远的呢，就是就是远在这个超辐射这个云之外来了一个伴星，然后这个伴星呢，它可以做到什么样事情？就是说它可以让这个322这个态和比如说其他的态，比如说300这两个态进行混合。那么如果322这个态和300这个态混合之后，会发生什么样的现象呢？因为前面我已经强调过了，就是说这个因为这个黑洞的这个超辐射的时候，这个它的增长率和不是超辐射的态，它的那个衰减率呢，它有巨大的差别，就是阿尔法的4L 次方。那么322这个态 L 等于2，300那个态 L 等于0，所以说一下就差了阿尔法的8次方。阿尔法的8次方，你比如说阿尔法取0.1的话，就是10的8次方。也就是说，这个指数增长的态和指数衰减的态，这个增长率是比这个衰减率要慢10的8次方啊。然后这样，你一旦旁边来了一个伴星，使得这个指数增长的态和指数衰减的态有微小的混合的话，那么这个混合一下子，你这个混合你即使有10的负8次方那么小的混合，也会使得增长的态呢明显的变得不稳定。这个就是所谓 termination of superradiance。然后这个具体的计算的话呢，这个具体的计算是量子力学里边一个非常标准的计算。具体的计算的话，就是说，因为旁边来了个伴星，那么来的这个伴星呢，我们就可以把它就是看成是哈密顿量里边引入了非对角的扰动。就是本来的话，这个哈密顿量你给它写成分离变量的形式，然后你给它写成这个322、300像这样的态，就相当于把哈密顿量对角化了嘛。来了一个伴星之后呢，就引入了哈密顿量里边非对角的扰动。然后哈密顿量里边非对角的扰动怎么解呢？这个如果要是我们求近似解的话，就非常的容易了。求近似解就是假定这个伴星，因为它离得远，离这个 cloud 比较远， 所以说呢，这个伴星它就可以看成是这个运动非常慢。然后我假定这个伴星不动，然后这个伴星在这个地方的时候，它产生的微扰是什么样子？给算一下，然后它导致这个衰变率就是有多不稳定。然后伴星在这个地方、这个地方，然后我分别在伴星不同的地方的时候，你把这个系统都解一下，然后最后呢，对伴星的位置做一个平均。那么这样的这个 static 的近似下呢，或者说 WKB 近似下呢，我们就可以很简单的把这个解析解给解出来。但是在 WKB 近似下，就是这个解的适用范围是比较有限的啊，因为我假定这个伴星不动，就是说如果这个伴星的这个运动的这个时间的尺度和这个 bosonic cloud 和这个引力原子外边的这个玻色子云它的响应时间的尺度如果要是接近的话呢，这个近似就失效了。但是这个时候我们也可以，如果要是它这个比较近，但是还不是特别近的话呢，我们也可以用一些其他的方法，就是用这个所谓 co-rotating frame，就是做一个参照系的变换，然后把这个问题给变成一个就是把这个就是考虑一个黑洞和伴星就同样旋转的这样的参照系，在这个参照系下可以让这个近似的精度变得更好，然后这样计算呢也可以更精确。好的，那么然后这个就是计算的结果。这个计算的结果呢，就是说这个第一个是说伴星和这个黑洞是同样旋转方向的，然后这个是伴星和黑洞旋转方向相反的，但是它们定性的结果都是相似的啊。就是说，你比如说这个是211的态，这是322的态。就是说211的态呢，就是说首先它可能还发生几个共振的，就是所谓 gravitational collider physics 的这个transition，然后呢最后就衰减掉了。这个衰减掉的意思就是说，因为伴星使得这个super radiance 的态和衰减的态之间有太多的混合，所以说呢，这个 super radiance 本来是指数增长的态，变成了一个指数衰减的态，它就不稳定了。那么对于像322这样的态呢，就是你甚至都没有机会去产生 gravitational collider physics 的那个波尔 transition 啊，只能产生精细结构 transition，然后就很快就变得不稳定了，不稳定就衰减掉了。当然，这个地方我们只画到了就是这个伽马开始变小，其实伽马开始变小以后很快就变成负的，但是因为我们这是对数的图，就没有办法画负的那部分，它是可以变成负的，然后变成衰减的。那么同样的这个图呢，也可以也可以画成这个样子。这个是什么意思呢？这个图里边这个 Q 就是黑洞的质量比，就比如说这个 Q 是10的负4次方，就相当于是这个伴星的质量是黑洞质量的就是1/1000。然后呢，这个图里边的这个颜色呢，表示的是在这个普朗克单位之下 RC 和 M 之间的关系，实际上也就相当于说是这个伴星是在多少倍的 Schwarzschild radius， 或者说这个黑洞的 horizon radius。这个伴星呢是在多少倍的 horizon radius 在这样的数量级上，比如说这个像比如说这样的这个黄的颜色的话，就对应着这个伴星呢是黑洞世界半径的，比如说是1000倍到10000倍。那么比如说我们看这个黄的这个区间啊，就是黑洞世界半径的1000倍到10000倍。然后呢，如果要是这个 Q 是这个10的负4次方，也就是说这个伴星的质量是黑洞质量的1/1000。然后呢，这个伴星的这个轨道也是这个黑洞世界半径的10000倍。即使是在这样的情况下呢，就可以，就是在这个 band，就是相当于就可以让这个322这个态从稳定的变成不稳定的。那么这个大家可能想，它为什么会这么敏感，会这么 sensitive 啊？就是你这儿有一个10000这样的因子，然后这儿又有一个10000的因子，就是这样的10000乘以100001亿分之一的围绕，就可以使这个super radiant 这个态变得不稳定了。这个就恰恰是因为刚才我们已经讲过的，因为322这个态的growth rate 和300那个态的 decay rate，他们俩就刚好差了10的8次方倍，你阿尔法等于0.1的时候，所以说就确实大概在这个地方就变得不稳定了。所以说这个和我们前边直觉的那个数量级估计都是吻合的。 那么对于322，对于像除了211这个态以外啊，就是211是那个能量最低的那个 super radiant state，这个 state 的话相对来讲还是比较稳定，我们这个效应不是很重要，因为你可以看到就是说，除了在很极端的参数区间，要不然的话我们都需要那个伴星的质量比黑洞质量还大才行啊。然后这个灰的区域，并不是说它不会发生 termination，只是说我们的近似区域态都是外边也围在这样的。当然，宇宙中你存在某种质量的标准场的话，反正宇宙中存在那么多质量范围的黑洞，所以说没准它可以有一个匹配的。然后我们讨论了这个所谓 termination of superradiance 这样的 effect，也就是说所谓的这个 off resonance 的这个就是伴星和黑洞周围的 effect 这样的和伴星和引力原子之间的相互作用。会使得引力原子除了211以外，别的态都变得非常的不稳定。那么211这个态是不是变得不稳定呢？这个我们还不清楚，因为我们的计算方法在211这个态上失效了。然后其实也可以考虑像这个resonance，这个 resonance 就是像鲍曼等人的文章里边算的，在这里我就不详述了。好的，那谢谢大家。大家如果有问题的话，我们欢迎讨论。哎，我看聊天窗口里边这是有问题吗？我看一下啊，没有，呃
我看线上有没有？等等啊，
线上没有，没看
啊，
见
不是，我说那个扣响上，哎，那
那个
个
我没注意。
扣响上面我看一下有没有。那先歇会儿，等会儿那个毛衣老
嗯，
师来了再讨论。
哎，好的好的，
好的，好的，你先，那你或者先挂着呗。
嗯，好。
哎，不是，现在应该是王一，看王一报告吗？
来来来，
哦，他在
讲完了，讲完了，偷
哎，
袭，不好意思啊。
没有没有，不好意思，
这个也是临时的，就看这儿有个空儿就来就来讲了一下。
好的好的，
他说你搞
我先把我那个东西架上啊，然后因为我看看能不能。
他先要架一下那个东西。 但是那个转换头你有没有啊？你的接口更好是不是？
对，我是那个高清的。
你就这样吧。你就我知道，不是你那啥，
我把
不是你先放着
啊，
然后你那个啥，
主要是网。
对，是网连上就行了。哎，这个对，就是这个接口。
有没有哎，对了，你是怎么的？
我来，你先接上。
对。
哎，有一个那个 cqu.net， 你找一下。
这个不行。
cqu.net。
在哪？这是什么？
对，你点一下。
这是重庆了。
对。哎，有一个弹窗，你把那个弹窗弹起来。行。
不选择吧。
对。哎，好了，然后你登到那个。
好。
这个接好了吧？
这个接好了。
我看到有一个问题啊，说是211态和311态的区别。那么这个就和原子物理里边一样的， 就是因为主量子数就是二是主量子数嘛，然后一是那个角量子数，另一个一是磁量子数，所以说211这个它的就相当于它是能量比较低的，然后311那个因为它的主量子数比较高，就跟就是原子一样的，所以说它能量相对高一点。然后能量高的话，其实这样的态 superradiance 产生率也相对小，就是它不容易产生出来。然后211是那个更加容易产生出来的。
你可以了。
行，OK，升起。
可以切了屏幕。
但是这块没不需要投屏吗？不需要投屏。待会儿有听众吗？好像没有投上去。
那都用这个。 这些的，然后他主要是研究这个，他们从这儿进。从这儿进，对，这个是清华大学天文系的茅奕，他主要是做这个再电离和那个21厘米线，然后主要是偏观测一些的内容，然后还有啥可进？啥？他是这个清华，不是北大，然后这个毕业，然后是这个你打开我念一下吧。
我找找啊，
OK，我介绍背一下我。这个毛毅，这个在这个北京大学获得学士，然后在麻省理工学院获得博士学位，然后在那个德州奥斯汀分校和法国巴黎天体物理研究所做博士后，2015年加入清华大学。是长聘副教授，他的研究方向是宇宙黎明和再电离时代以及宇宙学探针。尤其是21厘米宇宙学，它主要是研究工具是理论建模、数值和半数值模拟，以及利用机器学习进行数据分析。主持了科技部SKA 专项项目，入选了国家级人才计划。行，那个你可能得讲的科普一点，就是面向这种大一的学生。
好的。我切换一下。那个，谢谢周教授的这个介绍啊，然后哈哈，这个前面的灯可以关上吗？行，就对，把前面灯关上。那个，我稍微调一下。行，那个那个我今天录音，看看啊，录屏录制是吧？本地录制还是云录制？本地录制。我需要申请录制权限。对。
哎，魏家峰，魏家峰。
好，对，所以今天非常高兴给大家介绍一下那个宇宙再电离时代的一些物理过程吧，然后我们怎么想利用它去限制利用未来的观测手段去限制宇宙再电离的模型，还有宇宙初始条件。对，我今天本来是因为咱们现在好像线上也没有外国人，所以我就用中文讲。那个宇宙再电离它是这么一个过程，就是我们知道宇宙在婴儿期的时候，它是处在非常有激光笔吗？行，算了吧。宇宙是处在非常高温高压和高密的状态。那么这时候，当那个宇宙膨胀的时候，温度慢慢降下来，这时候宇宙充满这个38万年的时候，这个宇宙出现了这个微波背景辐射。那么这时候通过再复合的过程，宇宙中的这些原来的电离气体就复合成为了这个中性气体。那么这些中性气体它在经历了很漫长的宇宙学年龄之后，那么它在引力的这个自不稳定性下，它开始收缩，然后慢慢的形成一些非线性结构。那么里面就孕育了暗物质运，以及在里面孕育了第一代星系。那么第一代星系的出现还是个公开的问题。那么一般认为它是在这个宇宙1亿年左右的时候出现的，1亿年到几亿年的时候出现的。那么它们出现以后，他们会把这个宇宙中的这个原本的中性氢再次电离。那么这个过程呢，我们做了一个动画，这个可以。Okay. Okay, no problem. I can switch. So, so this movie is made from a simulation using the semi-numerical simulation code called Cirrus, developed by my student Meng Zhou and myself. So as you see, at this point is about 50% ionized state, where the blue regions are neutral regions and the red region are already ionized. So inside each ionized region, there is one or more first galaxies, and they emitting ultraviolet photons and X-ray photons, and approximately isotropically as in the beginning. So you will see more or less spherical regions and isolated. But when this more first galaxy form as the universe expands, so this ionized region will touch and merge and eventually percolate the whole universe. Sorry, let's see the movie again. So this is at the beginning where everything is ionized. Everything is neutral. And then you see this isolated ionized regions we call the ionized bubbles. So this is a three-dimensional show of this state. And then you will see this ionized region will grow and merge, and eventually ionize the whole universe. So after the universe ionized at about redshift 6, which is at the time of about 1 billion years old, this universe is filled with ionized gas, and with a neutral fraction below 1 part in 10,000. So it's very small fraction of neutral gas in the universe between the galaxies. So that's what we call intergalactic medium. But we can still have observe some neutral gas after ionization, but inside, not between the galaxies, but inside the galaxies or inside halos, because there they have a very high density and can accommodate a very high recombination rate. So this process from universe about 100,000 years old to 1 billion years old is what we call the Epoch and Reionization, and this is and this state is a very key phase transition of the structure formation, and particularly that is a feedback of the nonlinear structure back to the evolution of the whole universe. So so that's what we call cosmic dawn, meaning the beginning, the first light of the galaxies, and the Epoch Reionization. So that means the whole process. So this time, this period of the universe is not so late compared to our later universe, because our universe is 13.7 billion years old, So compared to our late universe, it's early, right? So you can basically at a late universe we can make a very large field of view galaxy surveys to map the whole universe. But in the early universe, as you know, we have a James Webb Space Telescope. In principle we can see the universe, see the early galaxies in this time, but in very small field of view. It's like a pencil-like field of view. It's very small, so we cannot make a large field of view galaxy survey like in the nearby universe. So observation of this early time is very difficult. On the other hand, compared to the early universe, like observation by the CMB, this time is late. So we cannot, from theory point of view, we cannot use very simple analytical formalism if we want to study the period accurately. Instead, we have to use numerical or at least semi-numerical simulations. So from both theory and observation point of view, this is a difficult period in the universe, and it's still a lot of questions to be explored. So let me summarize the indirect problem of the epoch reionization. So that's partly tell us information what we know about this epoch reionization. So landmark forest first. So landmark forest is absorption features of the distant quasar spectra. Okay, so when the photon from the distant quasar travels through our universe, when they met the neutral gas in between, there will be a landmark emission, landmark absorption by this neutral gas in the frequency of landmark photons. So these photons will keep cosmological redshift towards us. So when we see that, it's not a single line, but a series of lines. So that's why it's called landmark forest. The frequency or the wavelengths that we observed basically can reflect the cosmological redshift at the location of the neutral gas in the distant universe, and the absorption depth of the landmark forest basically can tell us the Gunn-Peterson optical depth, and that tell us this neutral fraction of the hydrogen at the time of the location of emission. So so the good point is the landmark emission is landmark absorption is very easy. This cross section is very big, so it's easy to see this absorption. But the bad thing is, as you see this cross section, the prefactor is very large. So even if we have a small number of the neutral fraction, then this optic depth is of order 1, and that means the suppression or absorption will be very large. And given the sensitivity of experiment, say here, then if the absorption is below this sensitivity, this threshold, then you will never see more absorption features. So that's why this problem is very sensitive to small number of neutral fraction. So in the classical paper by Fan Xiaohui in 2006, they observed this Gunn-Peterson optic depth as a function of the redshift, and so they find this optic depth has a rapid increment at about redshift 5.8-ish. And if we translate that number to the neutral fraction, then we know that we can know that the neutral fraction is basically about 10 to minus 4 at redshift 5.8-ish. But above that, because it's below the observational sensitivity, so you only see the lower limit. So okay, anyway, so from the landmark forest, we know the reionization finish at redshift 6, and finishing means we define that as the neutral fraction is below 10 to minus 4. And also, second probe is the cosmic microwave background. So basically, the photon of CMB will travel through the universe, but in the process, there will be a secondary effect. One of the most important is electric scattering of the photon over the free electrons. So that is the Thomson scattering. So this process is basically can smooth the temperature fluctuations. Okay, so because I scatter light on the other direction, but on the other hand, it will increase the polarization fluctuations because Thomson scattering basically can change unpolarized light to partially polarized light. So these two effects together can measure this optical depth. Planck basically measured the optical depth to be about 0.05. So this number means out of 100 photons emitted from the last scattering surface, 5 photons will be scattered during the traveling. So if we assume the universe is ionized instantaneously over the whole universe, and this redshift of instantaneous ionization from the Planck measurement is about redshift 8. So that is an apparent conflict with the end of ionization at redshift 6. So this simply just means we cannot model ionization as an instantaneous process, but it must be extended and gradual process. But how the history depends, it depends basically is beyond the scope of the CMB measurement, because basically the tau is only a integration of the photon of electron number over the light side, so you cannot tell much about details. Okay, and third probe is Lamar alpha emitters. Lamar emitter is basically a way that we can find the first early galaxies. So when you see a very bright emitters in the Lamar alpha wavelengths, so that is possibly an early galaxy, and that is because the inside galaxies, the stars will emit very high energy photons, but this photon will scatter inside the galaxy by the dust and the neutral bark of the gas, and so there will be many excitation, de-excitations, and out of that there is a Lamar photon scattered through that, and a very small fraction of Lamar photon will escape from the galaxies. Okay, and so that's why we can if it somewhere appear very strong emission of Lamar photons, that's possibly early galaxies. So people to quantify the Lamar emitter, people use so-called luminosity function. So that is so that is basically the number density of the Lamar emitters as a function of the Lamar luminosity. Okay, so you see this feature basically from low redshift to high redshift. This function keeps about same shape, but there is an overall suppression of the amplitude, and from like redshift 5-ish to 6-ish. So this is because as we in the early universe, when these photon escape from galaxies, they first met these ionized regions. Okay, and then if this happens after ionization, then this ionized region just simply going through the universe without rescattering. But during ionization, out of the ionized bubble is the neutral regions. So this Lamar photon will rescatter after they re-enter these ionized neutral regions. So that's why there will be a suppression of the overall amplitude. But then in this work in 2017, a larger collaboration led by Professor Wang Junxian in Keda basically find at the even higher redshift 6.9, on the basis of overall suppression, there is an enhancement on the higher luminosity end. So this enhancement is very interesting, and that is actually can be explained by our picture that universe is not ionized homogeneously, but instead is ionized in the bubble morphology. So basically, for the bubbles, when the ionized region escape into the ionized when the photon escape into the ionized region, but then into the neutral region, if the bubble is large, then this photon will have to travel and cosmological redshift at the same time. But then if the time of traveling is long, then when they re-enter these ionized neutral region, the cosmological redshift can be large enough so that this landmark photon frequency will be redshifted out of their resonance range. So which kind of luminosity which kind of emitter will have larger bubbles? Then that must be the heavy photons. Okay, the more massive more massive galaxies will have more brighter emission and will have more brighter bubbles of ionization. So they will have less suppression in this end. So landmark emitter, the enhancement in the high luminosity end basically tell us indication that the reionization is inhomogeneous, but in a bubble-like structure. So what I said is more about picture, because there are a lot of details depend on the models, but basically this is a consensus of what to know about the universe of the approximation. Basically finish at redshift 6, and it's a gradual process and it's inhomogeneous. But if you want to know the details, okay, so it's like a group of blinds touching the elephant, study the elephant on every aspect. But if you want to get an X-ray scan of the elephant, we need to have a tomographic probe of the universe. Sorry, 光深. Okay, so that is so optic depth is a jargon here in the astrophysics. Basically, so so basically what you observe is the intensity, okay? And you have an envelope of you expect the intensity, and that is suppressed by the optic depth by E2 minus tau. So this tau is optic depth. So that is basically tells you the suppression, how much suppression due to the absorption in the in between. Okay. So to make an example, basically, in many years ago, when Beijing is very dusty, okay, and the way that I can basically estimate the index of the what's it called, PPM 2.5 is the way that I look from my office to the main building of Tsinghua. Basically, if I can see the main building, then that means PM 2.5 is below 50. And if I cannot see that, that's about over 100 or below over 200. So that's the way you estimate optic depth, how much photon is absorbed along the traveling. Okay. Yes, exactly. So it's similar to the CMB optic depth, right? It's the integration of the electron density, right? It's similar. Okay, so that is opening. Yes. 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 Sorry. How long is the error bar? I'm not an observer of this group, but so yeah, from the plot you see basically at least it's some sigma of the trend over the trend. Sorry. Yes, compared to the red. This red measurement, that is 6.9. Yes. Yes, I think there are two Japanese group basically is also trying to measure that, but I think they didn't find. So there's some argument on this enhancement. So their point is this. Huh? So they put a filter in a telescope. I forgot which one in Chile. I forgot what name of the telescope. Basically, they put a filter to measure exactly redshift 6.9, the landmark photons. Huh? Some point unexplained. This one? Wow, this what? Yeah, I think you have to be not a perfectionist, both for theories and for experiments. Yeah, this could be a wrong systematics. Yeah. Anyway, yeah. So yeah. Anyway, I think they are accumulating data to, but this feature is very consistent with the theory expectation about the bubble homology of the UR.
Explanation for the bubble rather than the bubble.
I don't think so, because what you measure at this time is epoch coordination, and yeah, as far as I know, I didn't see other explanation. Again, inside this explanation, how this enhancement depends on the details of the morphology is very model dependent, because as you see, this is a very large error bars, and also this is this effect is a kind of a collective enhancement from many measurements. So it could be some selection bias or L is luminosity, yes. L, yes, that's the luminosity. Phi is not flux, is basically number density of the Landmark emitters. Number density of Landmark emitters. Yeah, so each bright thing. You can imagine like that. It's one bright source at this frequency. Yeah. Which one? This one?
Sorry, this is black. So this looks consistent with
yeah, actually I don't know actually. I can't remember this this kind of shape. Well, that's natural, because the more, well, basically in the universe, the massive photon, massive galaxies always have smaller population, right? Right. L luminosity, higher luminosity means massive galaxies. Yeah. But the number is small. The number is not the massive. It's not the mass density. It's the number density. No, that's not theory. This is observation curve. This is from different observations. Okay. Anyway, so let me just get to the point of my talk. So to study the neutral gas inside during epoch reionization more systematically, we need to have a better probe. So this is a cartoon of the how the neutral gas look like during UR, where you have these ionized bubbles and neutral gas. At the time, the gas is not hot. Basically, the temperature is 10,000 Kelvin. So you cannot. So this neutral gas cannot emitting Landmark or other photons by itself. But the strong probe from the neutral region is the neutral hydrogen 21 centimeter line. So because the 21 centimeter line is a hyperfine transition due to the between the two hyperfine states, if you consider the coupling between the electron spin and nuclear spin, and the ground state of hydrogen will split into two hyperfine states, the parallel states and anti-parallel states. Okay, when they have the spin flip, there will be a 21 centimeter photon emitting out in the corresponding to frequency 1.4 gigahertz. So that is a 21 centimeter line. And let me get back to that. And also, in the future, we could also use other molecular line intensity mapping to study. For example, for the CO, it's a rotation line. So that is also a possible spectral line to look into the higher universe. This wavelength is is about 10 to minus 10. So yeah, so it's about well, rest frame frequency is about over 100 gigahertz. So that's high, but this one is 1.4 gigahertz, and the redshifted basically. So the reason why 21 centimeter line is very useful is because it's basically is because the disadvantage of that. The disadvantage is the frequency. This transition is basically prohibited transition under the electron dipole, but it's allowed in the magnetic dipole. So that's second order transition, so that they have very small Einstein A coefficients. So this small number corresponds to a one-time spontaneous transmission in 32 million years old. So it's very, very small possibility. But in our universe, there's a lot of, the usual hydrogen is the most abundant element in the universe. So we can see the 21 centimeter line from the sky. Okay, so so on the other hand, this is a good thing for our observation, because you don't need to consider the reabsorption or scattering of the 21 centimeter line once it is emitted out. Okay, and also the usual hydrogen is inside the universe from very early times in the dark age to nearly today. So at a different time, so the emitting redshift frequency is 21 centimeter, but when we observe it, it's times 1 plus z factor. So it's basically redshifted to different bands of the frequency. About helium? Yeah, actually, helium reionization, there are also study of helium reionization, but that's you mean from the hyperfine transition of helium 2? In principle, yes, but that's even smaller strands. So this is a mock, not mock actually, a synthetic map that was made by of the 21 centimeter emission, the from simulation. So basically, at each place, each point of the universe, you have the emitting 21 centimeter line. But then when we observe it, you times the 1 plus z. So basically, you can, the frequency is 1.4 gigahertz divided by 1 plus z. So observed frequency is from 1.4 gigahertz down to even smaller than 30 megahertz. So it's very large range. So we just grab one part of this frequency band, so to show that this can in principle map the universe from completely almost neutral to appear these ionized features. So that is because first, from the wavelength or frequency, we can map back to the position in the light cone, and second, from the strength or the intensity of the 21 centimeter line, we can that corresponding to the energy, the photon, the gas density and gas neutral fraction and the temperature of at the time of this of the interest. So in principle, we can also make a detailed study of of the gas along the light cone. So that's why it's called tomographic mapping of the pseudo 21 centimeter line. And let me get back to CO. So why we also want CO? It's because as you see, there's a host. There's these ionized regions. In the ionized region, basically there's no 21 sigma emission. So in the 21 map, it's just it's a host. Then we cannot directly map the density inside that. I'll talk later that we can use indirect probes to study, but for direct probe we cannot study that. So if you want to make a mapping of the whole universe, cover all the positions, then we probably want other probes to fill those gaps, these holes. And this hole corresponds to where the first galaxy is, right? So first galaxy can be basically indicated by their signature on the feedback products like a CO or C2 molecular. So that's why, in principle, if you use CO lines, this is also from simulation, you can compare the positions of this is the holes of the 21 centimeter emission, but then that corresponds to the high density regions that can be very well traced by the CO or C2 molecular intensity mapping. So that's in the future. Of course, this is CO is more difficult to measure than 21 centimeter. But in the future, if we can have both observation, we can map the whole universe from the cosmic dawn to the epoch relation.
So it takes.
You mean this? Yeah. No, this is just the so this is a line of sight. This is a perpendicular to line of sight. A cut of the cross section. Yes. Yeah. Okay, so let me a bit speed up. Okay, so that's back to the 21 centimeter line. So because that is more interested in the recent years. So basically, the signal we look for 21 centimeter can be divided into 3 different categories. In the very base level, the average signal, which is the sky averaged temperature as a function of the frequency or redshift. But still, you can see some rise and falls. Okay, basically that corresponds to some different astrophysical process like this. This force corresponds to the formation of the first galaxies, and then when the universe is heated up by X-rays, this absorption feature right to the CMB background is smaller, and then the signal is getting from the negative to positive, and then when the reionization begins, that will the signal of 21 cm line will begin approach to 0, and this scale average measurement is basically done by the very simple antenna measurements like the edges and other experiment. So I think in 2017 there's a very famous result by edges that reports the observation of the absorption feature at redshift 17-ish or 16-ish, and but also the steps is much more larger than what is allowed in the standard picture. So in standard picture is about 200 milli-K, but they observe 500 milli-K. So some explanation, including the non-standard coupling between the dark matter and baronic. But anyway, so in I think last year the series 3 experiment claimed that at this sensitivity they didn't observe at 500 milli-K they didn't observe this feature. So whether this is real or not still under debate. But from theory point of view, the position of this absorption is there for sure. The only question is whether it is that deep. So that's not a focus on my talk. So, but then if we want to have some details on the clustering, basically how the Annans bubble is distributed, how the universe is structured at the early time, then we need bigger resolution, basically. Then we need to have the interferometers. So by interferometric arrays, you can increase the baseline, and so you can increase the resolution. Okay, so the first generation experiment basically measure the so-called the power spectrum. Okay, so that is power. I think most of people know, but for those who do know, so that is a Fourier space two-point correlation function. So that tells you how in Fourier space how two modes is how one mode is. Okay, so correlation function in real space basically tell you how two galaxies is correlated, how our density region is correlated. So in real space tells you over some separation how the density is correlated. So first generation try to measure the power spectrum, 21 power spectrum from the Epoch condition, but the best result they have is only down to here, but the theory is two order magnitude smaller. So this best result still assume the best the ideal removal of the foreground, and this is also only due to the thermal noise. To reduce thermal noise, the only way is to increase the size of the arrays. So we need a bigger arrays basically to achieve that. So two experiments is ongoing. One is HERA, that's by the US, and that is a experiment only for 21 centimeter observation from the EOR. And China participates in the square kilometer array, SKA. That is a international collaboration, basically. I think nowadays about 14 countries about that, and it's also very expensive. And it's beginning to construct from last year, and it's supposed to complete in 2028. So in principle, SKA will be the largest synthetic array interferometer telescope. So high resolution, high sensitivity, large field of view, high broadband. So everything's very good. The only drawback is slower than the HERA, because HERA got all the funds and had a very single target just to measure the power spectrum. So in principle, I guess in next 2-3 years, HERA will measure the power spectrum first. But if we want to make the mapping, so the ultimate goal is to map the EOR. So that needs a very high signal to noise, and that can only be made by the SKA. So that is the future of this field. Okay, yeah, this is my group. Yeah, I also have two people actually from Japanese, Taipei Mondona, and from Nagoya University. And also, my previous postdoc Hayato Shimabukuro is also from Nagoya, and now he is an associate professor at the Yunnan University. Okay, so for 21 centimeter observation, basically there's it's unlike the optical observation. The radio observation is very difficult. Data analysis, including calibration, foreground, frequency interference, R5 flagging, image making, foreground removal, and then you got the clean data. So basically, you got a whole big bunch of steps to get clean data. And so I'm not going to talk about these things. We also have done some work on these things, but let me focus on the scientific interpretation once we have the clean data. So that I guess most people in cosmology are interested. Let's get back here. First of all, if you have a power spectrum, what we can do? So this question is on the first side is easy to answer. It's like the you are given the CMB power spectrum and you are asked to estimate the cosmological parameters, right? That's easy. You just use MCMC to make this problem. Basically, this inversion problem. Once you are given software to calculate the power spectrum from a set of cosmological parameters. So for 21 centimeter field, there's a similar code called 21 CMC. So that is use the 21 centimeter power spectrum and to infer the simplest reionization model parameters from using the conventional MCMC method. There are two potential differences that can make this systematic. One is due to the bubble structure. Unlike CMB, which is a highly Gaussian field, this is a highly non-Gaussian field. So in principle, when you use MCMC, you have to assume the likelihood function chi-square to be Gaussian, at least some specific function, but most of the time you assume it's Gaussian. So that's one assumption on Gaussian on Gaussianity. And second, in 29 CMC, they basically in the covariance matrix, they basically only include the diagonal part and they ignore all the off diagonal. So in the sense that assume all the measurement at different k-bin or z-bin are independent. Okay. This also approximately valid for CMB measurement, but for 21 cm is problematic. But again, if you want to include all the z-bin and k-bin, this calculation is horrible. Okay. Anyway, so we try to fit on the image here. I think this is a large region with a large cosmic variance. So basically, probably it's not used by the constraint. Okay. Yeah, you have data, but you will have large error bars. So basically, this just shows how. So this figure just shows how a set of simple reionization model parameters can predict the power spectrum. Okay, and then if you are given the power spectrum, you can use MCMC to do the Bayesian inference. Okay. Sorry, why is what? Red, you mean here? It's very different. I guess in this model, so that is given a very. I didn't give the details, but for example, for the red, that assume the smallest visual temperature. Okay, small temperature means small minimal visual temperature. So that's smallest halo that can absorb. So basically, that hosts the more less massive galaxies. Small mass galaxies will be dominant. So that the expression is so that the reionization is less fluctuating. So you have the smaller power spectrum. No, then it's not necessary. This just shows a number of allowed regions in the parameter space. Okay, so let me also get back to the her point. So anyway, so recently these recent years, the machine learning began to become very popular. So in our field, Hitoshi Mabukuru and Benoit Semelin begin this application of machine learning to the field. So the first paper they use is just simple artificial neural network, where you have input the 21 cm power spectrum, and you want to get the reionization model parameters from the simple new ANN models. Okay, so in principle, they show that you can do this inversion problem with ANN, but the problem of that, they can only give the cross, so that is basically the best fit, but not the full Bayesian posterior inference. So in other words, you can only give this cross, but not the estimate of the errors. And this problem actually is not very easy to solve. In machine learning field, people don't care about the error bars, basically. So the group of people in AI in science care about that because we are scientists. So the error bars estimate is very important. But the problem when you look back that is still solvable. So when our group approached this problem, we realized that you can use a so-called simulation-based inference approach to SBI to solve this problem. So schematically, you are with a set of model parameters and some simulation, you are getting the data, so for example, image, but that's very high dimensional image data, which cannot be approached directly. You have to use some suppression to get data summaries. So for example, from data point of view, power spectrum is a way to, it's just one kind of compressor, okay? And then when you have the pair of parameter and the data summary, then you can use SBI to get a posterior. Technically, what you achieve, you can make this by nowadays have two different approach. The most popular one is called density estimation likelihood free inference, Delphi, and in this year also developed this called different approach, discriminative approach called neural ratio estimation. So let me just focus on the first one. So this idea is basically using the technique in machine learning called normalizing flow. Basically, given a non-Gaussian parameter space, then you can use a normalizing flow to map to a bunch of Gaussian parameter space. So each one itself is Gaussian, but you have a non-Gaussian, you have the nonlinear structure between them, and you use this normalizing flow to get the different weights of the different weights, and also means and covariance of each Gaussian space. So not one single Gaussian, but a bunch of Gaussian space. So that by this mapping, you can go back and forth between the non-Gaussian parameter space and the Gaussian parameter space. So that you can calculate the likelihood. So of course, using machine learning, you have to use the simulation to train to get a very large number of training samples to fit into the network. And once you have the likelihood, basically you can use the Bayesian theorem to get the posterior, because basically you know the prior. Okay, so this is so on this regard, we developed the so-called 21 Delphi PS. So that is using Delphi and to deal with the power spectrum, and we make a comparison of the result using the 21 MMC. So basically, the comparison, to make the comparison fair, both code is fed with the same power spectrum, 21 same power spectrum, and the underlying software of the simulator is 21 centimeter fast. And the inverted the marginalized model parameter is also same. Basically, the ionization efficiency and the visual temperature. So basically, only difference is a method. So as you see, our method, the green region, basically have a have better precision and accuracy. So basically, from the course position of course, and from the size of the credible region. Okay, so this is an example of two mock universe, a smaller mass dominated universe and a larger mass galaxy dominated universe. In both cases, our method outperforms. So basically, the PI of the 21 CMC, Professor Andrew Messinger, also test the result in a follow-up paper by them, and so basically their conclusion is so they still use the Gaussian assumption to do the MCMC, but then this time they include all the off-diagonal elements in the MCMC calculation, and they said they get similar results as using the Delphi result. But in that way, their calculation is very computationally expensive, and their conclusion is from efficiency and from both efficiency and accuracy consideration, it's better use Delphi as a new approach, a new better approach. So this is for power spectrum. Now, if you have an image in the long term, what you can do. So on that regard, as say, you simply need to get a better compression, because from data you cannot directly use data and parameter to do the likelihood calculation. Okay, but you have to use some compressor. So we first tried the 3D CNN. That's the popular architecture in previous years, and we got some results. But later this year, we found that you can use a better compressor called the wavelength scattering transform in 3D. So that's called we add the solid harmonic, basically the spherical harmonic basis. So the wavelength scattering transform can basically decompose the original field into different components. So and each one carries some different bit information of the original field. For example, for this first lower component, that is most sensitive to the boundary of the ionized bubbles. Okay, and in the second level, it's also, but not that keen. It's a bit smoothed, and in the same level, but in the higher order, you basically find it's kind of blurred some structure. So basically, this scattering transform is similar to the convolutional neural network, but it's kind of a fixed kernel thing, because they define a regulation of operation. Basically, you do the modulars, and then you do the convolution, and then calculate modulars and integration, and then that's the first level, and then you do that again for second scattering transform. You can do that, keep going, but basically you probably don't have much more information if you do that more than two levels. So we stop here at the two level of this compression. But using that, basically you see and feed those basically feed those coefficients into the data, and we get pretty better results. So that's the result in the scan transform is the purple one. Okay, so the purple one, and if you compare with the 3D CNN, the blue one is much smaller. The error bar is much smaller. And if you compare the purple one with the green one, which is using power spectrum, we find also that the purple one is outperforms. So this shows that first the purple the scattering transform is outperforms the 3D CNN in terms of the compression, and second the image carries more information than the power spectrum, so the constraint is better. I think let me just quickly go through the second. So in the second approach, it's called the neural ratio estimation. It's different from the first one. The different one is a generative approach, which you have to construct the neural network and train the network to get the likelihood. And the training process is most of the time very difficult and sometimes engineering. On different ways, discriminative way. So that is you're not training so you basically here you train a classifier. Okay, so for classifier you want to calculate, you want to maximize what they call entropy, and a theorem said when you maximize this given entropy, then you approach this the classifier you trained is close to the ideal one. So that is related to the ratio of the likelihood and the prior. So that when you get a convergent classifier, you got the ratio, and then using the Bayesian theorem, you can get from the ratio and the prior you get the posterior. So this two approach is consistent basically, and here we'll just do a test. Let's skip the details. So I use let me, if we start a bit late, let me use 5 minutes to explain what else you can do. Because what I tell you is we use a whole lot of information to study a few parameters that depend on models. But if you want to map, tell the universe and see how that evolves, then we better constrain how each point is look like at the beginning of the universe. So that's the initial condition reconstruction. So this is similar. It's in a similar spirit as cosmological initial density reconstruction using the local density galaxy surveys. So this is a famous work by Wang Huiyuan et al. It's called Elucid, and also the group by Jens and Wandelt using the walk code. So basically, so there they do the posterior calculation given the density, galaxy density in the nearby universe, and calculate the posterior of the initial density distribution using the Hamiltonian and MC method. Okay, so and then when you got the initial condition, you can use the FastPM to calculate the late universe distribution and compare with the observed data. So, but if you want to do the similar thing to the early universe, then it's difficult because I say there's almost no galaxy survey in the EOR Reionization. So what we can use is so here we propose use a 21 centimeter intensity mapping and CO or maybe C2 intensity mapping. So the idea is that, as I told, because they are comprehensive, the 21 centimeter basically is sensitive to neutral region, and of course it's also indirectly sensitive to the ionized region. But CO or C2 intensity mapping is sensitive to the high density region, which is inside the holes in the 21 centimeter maps. So in principle, they can comprehensive. Okay, so to make the reconstruction, you basically need two ingredients. One is approach to find the global minimum of the likelihood distribution, and second is you need to have a formalism to calculate the derivative of the cost function analytically, because in principle you cannot do that numerically. It's very time consuming. So here we by the way, cost function basically the negative of log of likelihood. So when you maximize likelihood, that means you minimize the cost function. So cost function basically defined as the sum of the difference of the deviation of the resimulated map from the mock map, modulated by the uncertainties. So here, anyway, so here we just go quickly. So we use a conjugate gradient method here. So that's a different approach from the Hamiltonian Monte Carlo. For Hamiltonian Monte Carlo, basically you sample the whole universe, you get a posterior distribution. But in our problem, we find it difficult to get converged for some reason. So here we use conjugate gradient, which directly finds the minimum of the distribution. However, the drawback of using conjugate gradient is you don't have a estimate of the probability because there's no posterior calculation. So you cannot guarantee what you find is a global minimum. It's only a local minimum. So it could be deviate in sense. And for the analytical gradient calculation, for this proof of concept calculation, we use a excursion set model of reionization, a very simple model to give the analytical expression of how neutral fraction is related to the Planck's fraction. And then for the CO, we're assuming that CO intensity is proportional to the star formation rate, and which is proportional to the Planck's fraction. So in principle, when you calculate the gradient of the cost function with respect to the initial density, you need three parts. One is the gradient, the derivative of the cost function with respect to the observable. So that is already there in the definition. And then how observable depend on the evolved density. So here is using the excursion set model of reionization. And then how evolved density is related to the initial density. Here we assume the Z-Wish approximation. So altogether, you can make an analytical expression. And to test, we make all this calibration using the analytical calculation and the numerical calculation. We find they are basically on the perfect line. Okay, so just show the result. Again, when you get the overdense region, you do the simulation again, so you can compare the input map and resimulating the map. So overall, for 21 centimeter CO map, this goodness of fit is basically within 7% in all the region, all time of reionization. And for power spectrum, it's most of the time the error bar is less than 4%. Okay, so only in very rare point it's above 4%. And this is a comparison of overdensity. At top one is the true overdensity, and this is the reconstructed initial overdensity. So visually, you don't see much difference. But when you calculate the calibration, so the reconstructed overdensity versus the true overdensity, you find for the early time reconstruction is mostly unbiased. Okay, so the mean is over 0. Residue is 0. Okay, but for the late time reconstruction, it's still a little biased towards the overdense region. Okay, so that is because maybe it's due to this our 21 centimeter signal is still sensitive to the neutral region. Okay, this is the power spectrum. Okay, so let me just stop here. So basically, we use a simulation-based inference method to form the posterior inference. So both from 21 cm power spectrum and from 21 cm images. And then we also propose to reconstruct the cosmological neutral density field from 21 centimeter and CO intensity mappings. And we developed this method based on conjugate gradient to get a goodness less than 7% at all stage reionization. So, okay, thank you.
I think what is very the next week.
Okay. So yeah, we're out of time a bit. Maybe let me end.
Okay, so 下面是个共享吗？哦，结束共享了，那我把这个发了。
Next speaker, Professor Han Yan is from Tokyo University.
Alright. Okay, cool. Can you hear me?
哦，你说还连上呢？哦，也可以。可以，没关系。那还是插上去。
因为我这个电脑。
你呢？
Good. Shall I start or? Okay. Oh, okay. Cool. Yeah. Thank you. First, thanks for inviting me to give the talk in this very interesting conference. Unfortunately, I cannot be there in person at the moment, but I will visit Chongqing later.
Yes, welcome. 要大全屏。
Okay.
So could you start with an introduction of yourself?
Okay. Yeah. Yeah. Hi, I'm Yan Han. I just became the assistant professor at the University of Tokyo starting this October. So before that, I did my undergrad in USTC and then my PhD in Okinawa Institute of Science and Technology. And then I did a postdoc at the Rice University. Yeah, and then I came to Tokyo. All right. Okay, shall I go on to give the talk or?
Yes.
Okay, yeah, cool. Good. So today I want to talk some of my work and also some of the work in collaboration with Christian Jepson and Yaron Oz. And the title of my talk is p-adic holography from the hyperbolic fracton model. So hopefully I can convince you that by the end of the talk, I can convince you that we have somewhat universal picture of all these holographic toy models in terms of holographic tensor networks and bit threads and so on. Yeah, and yeah, so I was saying that I'm sorry this time I cannot be there in person, but beginning of next year. Right. So outline of my talk. So I'll start by introducing a bit about quantum information perspective of ADS-CFT duality. And then people came up with some toy models to understand such quantum information properties. And mostly there is this bit thread model, and also there is this holographic tensor network. And both of them can, say, reproduce some of the features of ADS-CFT and tells us how information is entangled or encoded in this scenario. And for the third part, I'll talk a bit about my work on this so-called hyperbolic fracton model. And what we find is that there is an emergent version of ADS-CFT called p-adic ADS-CFT coming out of this hyperbolic fracton model at low temperature. And this picture seems to provide us with a somewhat universal, say, picture of all these different toy models. Yeah, so first, quantum information perspective of ADS-CFT. I suppose most of you already know quite a bit about this at least the popular science level. So the idea is that if you have anti-de Sitter space-time with the gravity living in it, and then on the boundary, there is a dual theory, which is a conformal field theory. So that whatever happens in the bulk of ADS is reflected or equivalent to something else on the conformal boundary theory, right? And so that this quantum gravity in higher dimension, which people have a lot of trouble coming up with a quantized version of it, will become just some conformal field theory in one dimension lower. And so in that case, there is no problem of quantizing the theory and study it in the perspective of quantum field theory. And so there are some very important properties or features of this ADS-CFT duality. And I'll use two of the most important ones. The first one is Liu Takayanagi formula, which is to say that if you have a boundary and you divide the boundary into two parts, say A and AC, and you can compute the entanglement entropy of these two parts of the boundary. And it turns out that the entanglement entropy will be proportional to the area, or in this 2D graph, it's the length of this, say, minimal covering surface gamma A, okay? And what is magical is that this does not only apply to the simplest case where you have just, say, one piece of A and another piece of AC. It applies to all the scenarios when, for example, A is divided into many separate parts, or for a thermal state, which correspond to some black holes existing in the bulk. Okay, so that's Liu Takayanagi formula, which is perhaps one of the most important formula for holography. Related to this, another very important feature is called rendular reconstruction. So the idea is that since you say there is a duality between the bulk and the boundary, then I can ask, given say some boundary information, how much of the bulk information can I reproduce? Yeah. So if we know all the boundary, then we know all the bulk. However, if we know, say, parts of the boundary, then how much of the bulk can we reconstruct? And renderer reconstruction tells us that the bulk you can construct is basically included inside this minimal covering surface, this green shaded region. You can, for this case, you can also call it geodesic wedge or entanglement wedge, WA. So basically saying that if I know part of the boundary A, then I can know, or I can reconstruct the bulk states inside the wedge WA. However, I cannot reconstruct any states in the bulk outside the wedge WA. All right. Now, if you think about renderer reconstruction, it is actually quite non-trivial, right? For example, if we say divide the boundary into 3 parts, A, B, C, and say we have some cutoff, then we have a center in the bulk, O, and we can ask how can we reconstruct the bulk state O at a location O. Yeah. So from the rule of renderer reconstruction, we know that if we just know A, then we can reconstruct the wedge on the upper left corner, right, which does not include O, right? So just knowing A is not enough to reconstruct the bulk information at O. And the same applies to just knowing the boundary section B or C, right? However, if I can know 2 of the 3 parts on the boundary at the same time, say again? Yeah?
I forgot about the definition of this wedge.
Yeah, the wedge is basically the region covered by A and its minimal covering surface.
You mean the volume or the area? Maybe.
Yeah, this WA, this green leaf.
Is the
thing.
area.
Yeah, in this 2D graph, it's the area here.
So what is the formula? Yeah, because I forgot the previous slide. Yeah.
Oh, okay. So let me go back a bit.
Yeah, the definition about the W, this wedge.
Yeah, the definition is, okay, so gamma A is the minimal covering surface.
Yes.
For A, right? And WA is what's like inside between A and gamma A.
Is that the volume or the surface?
That's a volume in the bulk. Yeah.
It's a volume.
Yeah.
The volume inside.
Yeah, it's the green. So on this 2D picture, it's this 2-dimensional region, right?
Okay. Okay. Please go again. Although I. Okay.
Okay. Yeah, so we will mostly just looking at a fixed time slice of the ADS space, and yeah. Okay, shall I go on or?
Please go.
Okay, yeah. So we were just saying that if I know just one part of the 3 boundary sections, then I cannot construct the bulk state at all. However, if I know 2 of the 3 parts, for example, BC, then the minimal covering surface is this line here, right? And the wedge is then the red region here, which includes O. So that is to say, knowing B and C, we can reconstruct the bulk information at O. And same applies to AB and AC. So you see here, how the bulk information O is encoded on the boundary is quite non-trivial, because if I just know one part of the boundary, no matter which part it is, I cannot have any information about O. However, if I know two parts at the same time, then I can have the information of O. Yeah. So so you can think, okay, if suppose I instead of working with field theory, I can just try to come up with some toy models made of, say, discretized qubits, and try to reproduce this kind of feature, right? So the idea is that the bulk information is some quantum state, say a qubit or some generic quantum digit called qdit. If it's has 3 states, it's a qtrit. But anyway, so the bulk state is some quantum state in some Hilbert space, and this bulk state is unknown to, say, 3 observers, Alice, Bob, and Charlie, and they correspond to these boundary sectors. However, we can encode this bulk state into some other quantum states that is in the hands of A, B, and C, and we want to encode this this qubit or qtrit in this case in certain way such that this kind of non-trivial encoding is achieved. That is, if Alice or Bob or Charlie makes his or her own measurement, they cannot know anything about the state in the bulk. However, if 2 of them make a measurement together, then they can get information of the bulk state. So there is actually an exact solution to this problem. So suppose I have a qtrit in the bulk, that is, it has 3 discretized states, 0 or 1 or 2. And then I can encode this bulk state in the following way shown on the equation here. For example, 0 is mapped to 0, 0, 0 plus 1, 1, 1 plus 2, 2, 2 in the hands of Alice, Bob, and Charlie. And so, and 1 and 2 is some kind of permutation of that. Okay, so now, for example, if you are, say, Alice, and you look at what you will get if you measure the qtrit in your hand, you will see that whatever the bulk state is, you always have equal probability of getting 0 or 1 or 2, right, in all 3 cases. So that is to say, if you're Alice and just do your own measurement, then you can have no information about what is the state in the bulk. However, if suppose you have both Alice and Bob to do the measurement together, then you can actually find out what is the bulk state. For example, if I get 0, 0 or 1, 1 or 2, 2, then I know the bulk state is 0. If I get 0, 1 or 1, 2 or 2, 0, then I know the bulk state is 1, and so on and so forth, right? So this mapping really satisfies this renderer reconstruction rule exactly. Yeah. In a more abstract sense, this is to say that we have some Hilbert space in the bulk, and we have some other Hilbert space on the boundary, and we want to define the mapping from the bulk Hilbert space to the boundary Hilbert space. And what happens is that the boundary Hilbert space is always larger than the bulk Hilbert space, so you actually use just the subspace of the boundary Hilbert space to encode the bulk Hilbert space. And of course, this encoding has to happen in a non-trivial way, such that this renderer reconstruction can be satisfied. And furthermore, there is some redundant space of the boundary Hilbert space that you actually don't use. So in some sense, you can think of them as corresponding to a bulk of a different geometry.
Excuse me, may I ask a question? That very naively, ADS-CFT is meaning they are correspondent, they are dual in the sense the Hilbert space wouldn't be the same size. So why the boundary is larger than the bulk?
Yeah, that's a very good question. So I think what is happening here is that this is a toy model of the so low temperature sector of the correspondence. And so if you have, and because of the nature of this, say, a tensor network, it corresponds to a fixed geometry in the bulk, right? So so suppose you are you write down some kind, this is a tensor network. So suppose if you write down some other kind of similar tensor networks, then what happens is you are only defining the duality at a very low temperature. Now, if you go on to higher temperature, you will need to change the geometry of the tensor in the bulk, right? For example, having black holes, which correspond to having some dangling legs in the bulk and so on, and that will gradually use up all the boundary Hilbert space. However, that you need to change the configuration of the tensors. Yeah. Okay. So now let's move on to talk about some toy models that reproduce this.
You must have this tensor network to have this kind of a picture.
I say again?
I wonder, you must have this tensor network to have this kind of a picture.
I suppose, yes. I mean, any kind of mapping from the bulk to the boundary can be written as a tensor network. If that's what you mean. Okay. Yeah. So now let's move on to some toy models that reproduce these holographic properties. The first one is the Liu Takeyanagi formula, which tells you that the entanglement between A and AC is measured by the area of gamma A here. So one of the, say, most, I would say, simplest way to have a picture that makes this happen is this so-called bead thread construction. So the idea is basically you have these line objects on the, say, hyperbolic disk or a slice of your ADS space-time, and on each line you have some entanglement going on there. So what happens is basically at the end of at the two ends of this line, you have some entangled qubit, say up, down, plus, down, up. So basically that's to say this line gives you like 1 unit of entanglement entropy. And suppose I have some evenly distributed flow of all these lines in my ADS space. And then I look at, for example, the flows going from A to B. Then because it's evenly distributed, so first the entanglement entropy between A and B is simply measured by counting how many of these entangled pairs do you have, which is to measure how many of these lines do you have. And then because they are evenly distributed in some sense, then the number of them is then constrained by the, say, bottleneck when you go from A to B, which is exactly the minimal covering surface, right? So
why you need this arrow?
You don't. Yeah. So this is just. Oops. So this is just showing the lines that go from A to the complement of A. Yeah. So they're kind
this is just entangle. Why you need start inside A?
Yeah. So because you want to measure the entanglement between A and the complement of A. So yes, so there can be lines going, say, from A to inside of A, or from, say, B to inside of B, but then they don't contribute to the entanglement entropy between A and B.
Please continue.
Okay,
Oh.
so yeah, so if you think about discretized lattice, you can think of each one of the geodesic has an entangled pair of spins at its ends, and then the entanglement entropy between A and B is simply to count the number of these orange geodesics, right? Because if it's inside A, it doesn't contribute any entanglement entropy between A and B. Right. So, and the number of this orange geodesics is exactly the minimal covering surface, or the, say, the bottleneck if you want to go from A to B. Okay. And suppose, so now I choose this sector of boundary to be A. If I choose another sector of boundary to be A, then I just find the other bottleneck. And so then they generically satisfy this Liu-Takeyanagi formula. Okay, so yeah, so now move on to the renderer reconstruction. I just already gave basically, say, a simplest example realizing the renderer reconstruction by using this Q-trait mapping from bulk to the boundary ABC, right? Of course, then you can just follow the same, say, spirit and write down more sophisticated tensor network. So what happens here is that each tensor here, this blue object has one leg in the bulk, which is the red thing here, and then it has 5 legs on the boundary. And it basically realized the renderer reconstruction when you divide the boundary into 5 parts. And then you can also contract these tensors together, so they tile up in the entire hyperbolic space like this. So in this case, then you have many bulk legs shown as the red ones, and then you have many boundary legs as the white ones. Then you define a mapping from the bulk state from the bulk Hilbert space to the boundary sub-Hilbert space. Yep. And so here on this holographic tensor network, if you have these bulk legs, then it defines what we call the holographic code. A code basically means mapping from one Hilbert space to another, and here is from the bulk to the boundary, right? You can also fix the inputs on the bulk legs. Then what you have is just the boundary legs dangling there, and they define a pure state, a pure quantum state on the boundary, okay? And by doing that, what you get is a holographic state. So that's just a quantum state on the boundary. So in fact, if you define these holographic states using these tensor networks, then you can actually check the entanglement entropy between a bipartition of the boundary, and you will find that they also satisfy the Liu-Takeyanagi formula. Okay, so so this all seems a little bit abstract, but then some really nice work done by Alex Zhang and Isert and collaborators sort of illuminated us what is exactly the entanglement structure inside these holographic tensors. So what they do is they, so on each leg here, you have a qubit. You have a qubit Hilbert space, and what they do is they map the qubit Hilbert space into 2 Majorana fermions. And then whatever state is defined by this tensor, so suppose I fix the bulk leg input, then I have 5 qubits. I have some state defined on the 5 qubits. Then this state turns out to be expressed in terms of the pairing of these Majorana fermions, which is shown as this kind of blue line connecting them. So, so for example, you have 2 and 7 paired together and 1 and 6 paired together. And the Majorana fermions belonging to different pairs, they don't talk to each other. Okay, so now you can then tile these tensors together to form this tensor network and contract these Majorana fermions, what you get then is the following picture. So what you have is, for example, the line here correspond to a pair of Majorana fermions that is entangled on this one end here and the other end here. And in fact, you have two pairs, but that's not so important. And along another geodesic, you also have these pairs of Majorana fermion entangled together. And on top of that, the different pairs, they basically don't talk to each other. So that is to say, the holographic tensor or the quantum state or the holographic state it defined turns out to have exactly the same picture of bit thread distributed on the hyperbolic lattice, because when you have these pairs of Majorana fermions entangled together, that's exactly, in the qubit language, that's exactly something like up, down, plus, down, up. Yeah. So in this way, it's of course then not surprising that that will give you Liu Takanagi entanglement entropy and so on. Now, these toy models are very interesting.
Here, when you are talking about the Majorana fermions entanglement, so do you mean there are real particles on the boundary, or it is the vacuum excitation? It's just out of vacuum, so similar to the Rees-Yama theorem.
Yeah. So first, there is no Hamiltonian here, so it is really, we're really just talking about some quantum state. Right. So these are some quantum state defined on the degrees of freedom living on the boundary. And this quantum state is written as this entangled pairs put together.
So that means actually you put some real fermion particles on the boundary instead of just the vacuum fluctuation.
Yeah, it's just the vacuum. Yeah.
Just the vacuum.
Just the vacuum state.
Yeah.
You can.
So it is similar to the Rees-Yama theorem, saying that the vacuum can be considered as infinite number of EPR pairs, something like that.
Yeah, exactly. So this process is exactly trying to what they call this entanglement distillation, which is to rewrite the state in terms of these EPR pairs, so you know what's the entanglement structure.
Yeah, thank you.
Okay, good. Yeah, I actually didn't know that. Thanks for the comment.
So you must have a fermion, Majorana fermion.
You don't necessarily have to. So here is just for this particular tensor. With qubit on the leg is easy.
Other type of particle.
Yeah, it can also work. What you need really is just some discretized Hilbert space, and that's pretty much all. Yeah, it's just in this particular case, using the Majorana fermion is like simpler. Yeah. Okay, good. So now this all this works.
Sorry.
Yeah.
So in this bits, can you go back to the previous slide?
Sorry, I cannot hear.
Can you hear me?
Okay, now it's better.
Okay, now I'm seeing. So in this bit set picture, you are assuming scale invariance of entanglement structure.
Scale invariance.
So can you go back? Okay, so for example, can you go to the next page? I think.
You mean previous one? Oh, sorry.
Yeah. So
here.
Here you have some. Yeah, I can see some scale invariance in this cartoon.
Right. Yeah. So if, for example, if you move your center to somewhere else, then you will have the same picture.
Yes. And this is why you obtain ADS dual.
Exactly. Yeah.
And do you have some similar model for ADS black hole, like excited states in the bulk?
Yes. Right. Actually, in this tensor network papers, they discussed what is a black hole. And the simplest way to create one is to simply remove some tensors here, and then you just have some dangling legs in the bulk, and they will be the black hole microstates.
I see.
And then these black hole microstates are then mapped to the boundary states again.
Okay.
Yeah.
Thank you.
Yeah. Thank you. Right. So now we have all these very nice toy models that reproduce this Liu Takanagi formula and render reconstruction and so on. However, they are basically defining some quantum states, right? Either or quantum code for the bulk or the boundary Hilbert space. The question is really, for example, if you talk about ADS-CFT, then I can ask, what is the bulk theory, right? What's the bulk Hamiltonian and so on? And because these are just some states, so they don't have anything to do with the bulk theory or the bulk, what is the bulk theory? What's the boundary theory and so on? And so our proposal is that it turns out that these quantum holographic states are related to this so-called p-adic ADS-CFT living on the hyperbolic space. And and also this p-adic ADS-CFT, with many copies of them put together, will become the low energy sector of a Fracton model. So that's what we discovered, and I'll try to explain that now. So the toy model in our case is actually extremely simple. You can have different tessellations of the hyperbolic lattice characterized by this number PQ. For example, 5, 4 means 5 means the plaquettes have 5 edges, so they are pentagons. And Q equals 4 means you have 4 pentagons meeting at the same vertex, right? So this is going to be one important example I use later. Another important one is PQ is 5, 6, which P is 5 means, again, the plaquettes are pentagons, and Q is 6 means we have 6 pentagons meeting at the same vertex. Yeah, and you can have generic PQ tessellations as long as, say, 1 over P plus 1 over Q is smaller than 1/2. So we only really require Q to be even. So the system is well defined. And here we have degrees of freedom living at the center of these plaquettes. I call them Z, and they can be Z2 numbers or integers or real numbers. And going to different limits, or choosing different degrees of freedom just give you, say, different versions of the theory. And the Hamiltonian is a classical one. It's quite simple. So around each vertex, we always have even number of Z's. So we have the Hamiltonian is simply Z1 minus Z2 plus Z3 minus Z4 square. And then I sum over all the vertices. Right. For the second tessellation, it's 1 minus 2 plus 3 minus 4 plus 5 minus 6 squared. And then I sum over all the vertices. So that's just a simple classical model. So now there is actually a huge symmetry for this model because it's such a fine-tuned model. So the symmetry is what we call a subsystem symmetry. And the symmetry of the Hamiltonian is obtained in the following way. So at each vertex, for example, here, I can choose Q over 2 legs. In this case, I choose 3 legs that are not adjacent to each other, right? So these 3. And then once I reach the next vertex, for example, here, I repeat the procedure. And because I have to choose, say, half the legs, and I already have chosen the first one. So then once I choose the first vertex, or the first 3 legs in the first vertex, then the other legs that are going to be chosen are determined already. So by doing this procedure, for example, I can generate this blue degree 3 fractal tree, right? Of course, there are many of these trees living on this lattice. The red one is also an example. Right? So the subsystem symmetry is the following. I select one of these trees, for example, the blue one, And then I can select a region or a wedge that is covered by this by the branches of the tree. For example, this one here, the blue shaded region covered by blue. And then the subsystem symmetry is the operation of increasing the value of z here, all the z's inside this region by a constant. Okay, and why is the symmetry? Because on the vertex here, I have say this is let's say z7 minus z8, right? And because I increase their value by a constant number, then of course the vertex term here remain invariant. And then for the other vertices, they are either living on the edge here, they are living on the say corner of this wedge, so it's the same like z7 minus z8, or it's all of them are all included in the wedge, so it is, so for example, all the 6 z's increased by the same value. So no matter which case it is, the Hamiltonian will remain invariant. Okay, so then we have a lot of these symmetries. We first have many trees, then for each tree we actually have many of these blue wedges, and each of these wedge form its own contribute like one freedom for the subsystem symmetry. In the extreme case of Q equals 4, or the 5-4 tessellation, then this degree Q over 2 tree is simply a degree 2 tree. And then what happens is you don't have this tree structure anymore. Instead, when you select this tree, you simply just select this geodesic or straight line on the hyperbolic disk. And then you don't have so many wedges for one tree. Instead, you just have one wedge on the left and one wedge on the right. So basically, this is sort of extreme case of the generic tessellations. Okay, now the subsystem symmetry is kind of important here because in some sense it's the most essential thing, because it always acts both on the boundary and on the bulk. And for say different parts of the boundary, it acts on different parts of the bulk, right? So that gives you some flavor of this ADS-AFT duality already, but of course it's going to be more concrete. And also, just to briefly mention, if you want to have, say, excitations, what you can do is to choose, say, 2 trees that are intersecting, and then you increase the value of, say, z degrees of freedoms inside this green wedge by a constant. Say if you are spin half and down, you just flip these spins, and then you create a single excitation for the vertex term living here, right? Because as using the argument I just showed before, all the other vertices, their energy remain the same, except this one is in a higher energy state. And similarly for the 5-4 tessellation, you do it like this. And so these are called fractons. For some historical reason, but the essential feature is that you cannot move these fractons freely, in the sense that if, for example, I want to remove this fracton, then maybe, okay, I think I can, I may say, okay, if I flip this spin, do I move this fracton here? But the problem is if you do that, you create more fractons on the other corners here, 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 and here, right? So there is no way to flip just a local patch of spins to move this excitation somewhere else without creating more fractons in this process. This becomes kind of important in condensed matter. So for this fracton order and fracton states become a kind of important direction in condensed matter. But for us, it's not so important. We are really just looking at the low energy sector where we just do not want to have any of these excitations. We just stay in the ground state manifold. Okay, now, as I just mentioned, it turns out that this tree structure turns out to be very important. And then you can actually define some geo theory where your degrees of freedom live on the edge. I call them E, instead at the center of these plaquettes. And the definition is relatively simple. For example, for the electric, well, I call E because they are going to be electric field later. For the E here, it's sandwiched always between two plaquettes, right? So it's ZP1 minus ZP2 with direction given. And the direction is just simply defined in a consistent way. That is it. And now you can look at these vertex terms, ZP1 minus ZP2, blah, blah, blah. And for example, in this case, what you have is ZP1 minus ZP2 become E1 on this blue edge. And then ZP3 minus ZP4 is this E3 on the second blue edge. And then you have the E5 on the third blue edge. Sorry, the notation is kind of complicated. But in the end, what you find out is that this vertex term becomes simply the divergence of E square, not on all the 6 edges, but just on the 3 blue edges, okay? If you stay in the low energy sector, then that's what you need. Of course, if you go to the high energy, if you think about excitations, then the divergence of E on the blue edge has to equal the divergence of E on the red edge. But if we just ignore any excitations and we stay in the charge-free sector, then this condition is the only thing that matters. And now you see that in some sense, then the E1, E3, E5 are coupled together, and they are decoupled from E2, E4, and E6, right? And if I keep doing this on all the vertices, what I have is then the following. So first on the blue tree, what I have is some kind of a divergence-free condition or Hamiltonian that's costing energy for having charge of divergence of V on for all the electric field on the blue tree. However, they are decoupled from other trees. So I also have another theory of the same type that is defined on the red tree, okay? And then, of course, I have many, many other trees on the hyperbolic lattice. And the thermodynamic limit is infinitely many trees. And in the end, this hyperbolic fracton model just become this electrostatics theory on every tree embedded in the hyperbolic space. And now, previously, we talked about subsystem symmetry as flipping changing the values of the z's in this wedge by a constant. And that simply becomes introducing, say, electric field line on one of the tree. And remember that, for example, if you stay in the ground state where you do not allow any charge to appear, then of course you have to have this electric field line goes from one side of infinity to the other side of infinity. It cannot end in the middle of this tree, right? So that is just going from one charge-free electric field configuration to another charge-free electric field configuration, right? And that's the minimal way of doing that. So the subsystem symmetry has a very natural explanation here. And here you can already see some features of rendular reconstruction. For example, if I know the boundary electric field, say E1, E2, E3, E4, then by the charge-free condition, I can reconstruct the value of E5, E6, and E7. And here I reach the bottleneck that covers this part of the boundary, right? And for exactly the same reason, if I go beyond E7, I have freedom to choose what is the electric field here, even if I have the charge-free condition imposed on every vertex, right? So that is the rendular reconstruction stopping here. Okay, now, for example, if I come back to the extreme limit of Q equals 4, where my fractal trees simply become these geodesics, then what I have for this case is simply I have many of these geodesics living on the hyperbolic lattice, and each geodesic I have this electric field line, but because it's just a straight line, so I can say have the electric field on this line to be uniform, right? If I do not want to have charge on any vertex. So for suppose I choose Z2 degrees of freedom, then the corresponding electric field line is going to be either pointing down or pointing up, right? And this goes from one end of the boundary to the other end of the boundary. That is, if I know, for example, this bit of the boundary, then I know the other bit on the boundary, which is essentially a classical analog of entanglement entropy, right? So that is to say, each geodesic here has its arrow aligned in the same direction for the ground state. So that's simply a classical bit thread. And then also different bit threads they live independently from each other. They can choose their own direction, right? And that's exactly the, say, classical limit of this bit thread picture I introduced before. And again, to compute the entanglement entropy, or in this case, a classical case, you can also compute mutual information. It's about the same thing in our case, is again to look for, say, the bottleneck of this bit thread flow going from A to B, which is exactly the Liu-Takeyanagi formula. And the bottleneck is the minimal covering surface, right? And also talking about renderer reconstruction, you do not only have it on a single tree, you actually have it in the entire bulk as well. So let me use the 5-4 tessellation as an example again. So suppose I know some boundary side and I know the bulk side, and this time let's take them to be Z2 degrees of freedom. So it's either spin up or down, right? So in this case, for the Z2 degrees of freedom, this vertex operator can be rewritten as simply the product of these 4 spin up and down with value +1 and -1, right? And then, so if I know I'm in the ground state and I know these 3 spins on the boundary, and I know the product of these 4 spins, then naturally I know the 4th spin here. So this is one step of reconstruction. And so now suppose if I know a section of the boundary, I can simply do this reconstruction over and over again. And each time I do it, I can know, say, a layer of spins inside, but that will stop when I reach the minimal covering surface. And again, this is because now I have 2 spins outside the vertex, on the vertex that is unknown at the same time, right? So this kind of reconstruction rule does not apply anymore. So when I reach the minimal covering surface, reconstruction stops. So the renderer reconstruction rule, which is to say that I can only reconstruct the bulk size inside the minimal covering surface, happens again, right? So again, of course, it's a discretized lattice model, so you will have some small corrections if you choose somewhat irregular boundaries. But that is not so important. Okay, so I was talking about p-adic in the beginning, or the title. So how is this related to p-adic ADS-FT? So p-adic ADS-FT, and then later Gubser and some other collaborators and also some other people start to figure out that this is kind of important toy model of ADS-FT. So what happens is the following. I have, again, the geometry is, I have this fractal tree structure as the bulk of the ADS. Right, and then this fractal tree extend to infinity, so that if I have a cutoff, these are the dangling branches are the boundary bits. Yeah. So there is a bulk action. You have these degrees of freedom living on the vertices this time. And the bulk action is simply, say, x1 minus x2 squared and summed over all the edges. Right? And so it's like the simplest action you can write down. Right? And then what Zabrodin found out is that you can actually write down an exact boundary action that corresponds to the bulk action. And the boundary action is the following. So again, here phi is essentially the x, the big X fields living on the boundary legs now, or the boundary endpoints here now. And then he find out that the corresponding boundary action is this, is written in this form, where both dx and dy integrate over all the boundary. So you have somewhat all-to-all interaction for all the fields phi, for the field phi living on the boundary. And this interaction strength is defined as x minus y p square. So here x y minus y p is the p-adic distance, meaning that it's the travel distance from x to y if you have to travel on the tree, right? So there is a unique path from x to y, and for example, in this case, is this, and that is the, say, the distance defined in this way. And of course, you see that if I have x here and say y here, then their travel distance is small. But if their y is here, then their travel distance is large. And so what Zabrodin find out is that if you solve the model in the bulk, and then what you get is exactly the model on the boundary, which is kind of rare case where in ADS-FT, you know exactly the action in the bulk and in the boundary. So this is the simplest model, and then later Gubser and other people developed a much more, say, sophisticated version of it. But what we need is just the simplest scalar model here. So if you look at the equation of motion for this model in the bulk, and that will be the Laplacian of x equals 0. For example, the Laplacian of x defined on vertex 1 would be 3x1 minus x2 minus x3 minus x4. And now if you think about x as the electric field potential, then the Laplacian being 0 is exactly divergence free condition if you define the corresponding electric field that live on the edges, right? And as you may remember, this is exactly the state we have on the tree, right? The ground state we have on the tree, which is this divergence free limit for the p-adic ADS-CFT. However, remember that we have actually many copies of these trees. So what we have is actually many copies of p-adic ADS-CFT that are sort of evenly distributed on the lattice, okay? And okay, so now come back to the final picture. What we discovered is that for the 5-4 tessellation, the simplest case, the hyperbolic fracton model corresponds to this bit thread picture, or at least the classical bit thread picture. And in the meantime, this is, in some sense, a trivial case of this p-adic ADS-CFT, where you don't have a tree, right? You simply just have a geodesic. And this picture is the classical limit of this quantum bit thread with entangled pairs of, say, spins on the end of each line. And again, this quantum bit thread picture is exactly the entanglement structure of a holographic tensor network. So we see everything here is sort of connected together very nicely. And you can say, in some sense, that for this holographic state, it is the the ground state of, say, a quantum version of the p-adic ADS-CFT, but it's not just one p-adic, it's many of these p-adics put together on the lattice. And now we know what is the bulk theory corresponding to this. And of course, that's the simplest case. More generally, you have these fractal trees instead of geodesics, where we have the fracton model that's equivalent to this p-adic ADS-CFT that are distributed on the hyperbolic lattice, and then we are doing some ongoing work to study the tensor networks that correspond to this sort of more general tessellation. Okay, and what we find is that in the Majorana fermion language, this kind of tree type of entanglement structure is exactly what you expect from this p-adic tree picture. That is, if you look at this bright blue picture, this is exactly this kind of picture, say, corresponding to the blue tree here, where you have Majorana fermions at the end of all these at the ends of the blue tree, and they are entangled together. And then on top of that, you have many different copies of trees that sort of live independently. Okay. So I think this is kind of nice in the sense that we have a somewhat unifying picture, understanding what exactly is the holographic tensor network in the sense of what is the bulk theory, and how to understand the entanglement structure and so on. And so that's the, say, take-home message of my talk today. All right, thank you. Yeah, I can take questions now.
Any questions? And yeah, and if there are questions for Imao or Iwan's talk, we can also discuss. Let's see. What is this attic?
Oh, so p-adic is a way, it's a term in mathematics where you are measuring, so first we measure the distance between numbers by simply their distance on the real line, right? But this p-adic distance shown here is also a consistent way of defining distance between two numbers. And it's a bit hard to explain. So basically, it's measured by the difference.
It's a kind of a measure.
Yes, it's a measure, and that is completely different from the real number measure. It's basically measured by their modulo of some prime number p.
Like a discrete version of distance.
That is correct, yes.
Okay.
Yeah.
Okay. So I have a question. So for k equal 4 case, the tree was geodesic.
Yes.
So this means that the bulk theory is GR, general relativity. And if you consider more general Q, it's probably different from Liu Takayanagi formula type thing. I mean.
Oh, so you still have the Liu Takayanagi formula because
area law?
Yes, yes.
Even though it is not geodesic.
Even though, yeah. So having this kind of geodesic, say, qubit entanglement is just say necessary condition. but it's not. It's not. Oh, sorry. It's sufficient, but it's not necessary. So, for example, here, what you have is essentially that, say, these 8, say, spins on the end of the tree, of the blue tree, are entangled together, right? So suppose if I cut my boundary into 2 pieces where, say, some are on the left and some are on the right, then they will have 1 bit of entanglement that is essentially delivered by the branch of this tree here, right? And now if I make a general cut of the boundary, and then I want to count the entanglement entropy between A and the complement of A, I am going to, what I need to do is to count the number of trees that go from A to the complement of A, right? And then because these trees are distributed evenly on the lattice, then it boils down again to look for the bottlenecks of this tree distribution, which is again the minimal covering surface. Yeah. Yeah, so that's what we think might be interesting, is that beside bit thread, you also have this bit tree entanglement structure, and they can also give you this Liu-Takanagi formula and so on. And
for example, if you consider stringy correction to GR, there is correction to area law.
Yes.
And this should be captured by something in this context.
Yeah, so that's something we are still looking into. So one issue with this lattice model is that because the lattice is already discretized, so this discretization already contributes some correction. But I don't think they correspond to anything real in ADS CFT, right? So the question is then, how do you distinguish the corrections that has a holographic counterpart and the corrections that just because of the discretized lattice effect? Yeah.
I see. Okay. Thanks.
Thank you.
And
Excuse me, can I ask a question?
Yeah.
Sorry, I still don't understand, but bit threads model shows that kind of ADS geometry arises naturally from entanglement structure, right?
Yes. Yeah.
But then, if you change the structure of entanglement, then the different is it possible that different geometry can arise? Is it possible?
So yeah, so again, I would think bit thread is sufficient, but not necessary. So yeah, I don't know if you think about this bit tree.
Yeah. So okay, I see. Thanks. So there's no, you mean there's no example other than ADS, right?
At the moment, no.
Yeah. Thanks.
Okay, thank you.
I think some people had proposal about connection between DS, CFT, and tensor network rather than ADS. Do you have any comment on this from this point of view?
Yeah. So, well, I just know a bit about this proposal. So so for the picture you are looking at, all the tensors are the same. And so up to rotational symmetry, they are just uniform and isotropic. So it is natural to think of them as embedded in this spatial slice of ADS. So for this DS CFT correspondence, I believe they are using this Mera tensor network, which actually has the tensors there are not isotropic. Instead, it has kind of a preferred direction in some sense, and from that perspective, it is actually not proper to put this Mera network in the isotropic spatial slice of ADS. And so what I know is instead you should embed the Mera network on the ADS, sorry, on the de Sitter spatial slice, and then the structure goes more consistently with the structure of the space then goes more consistently with the structure of the tensor. Yeah.
Okay. Thanks.
Other question. If no, we can end this session.
All right. Thank you.
Yeah. I think this you can use this room for discussion, and we go to lunch.
Okay.
And yeah, I think people, if you can leave, and people can leave or stay, and or just a free discussion, use this room. And we start afternoon at 2 p.m. 杨涵
Yeah.
把那个你的 PPT 能给我吗？不是，就是我就是自己看一看那个，因为
可以。
那个办会，然后有时候回消息，然后有的点儿没听到。
OK， 我把这个发给你，到时候。
然后到时候你最近忙吗？
我后面2周可能比较忙吧，因为那个。
那对，那没事，那就发信息给你，然后你把那些信息发给我。
信息指的是什么？
是什么那个？对，然后你下次啥时候来的？
我是1月底2月份的时候过去你们那边。
那你能路过北京吗？
我